Welcome to another Fix Latam High Energy and Mathematics seminar. Today, we're honored to have Professor Miguel Montero present the talk, Introduction to the Swampland, Part 1. Just a kind of reminder, the second and the third part of this lecture will be given on Wednesday and Saturday separately at the same time. Miguel Montero is a theoretical physicist specializing in string theory, quantum gravity, and black hole physics. He obtained his PhD in 2016 at UAM. He focused on Swampland program, which aimed to distinguish consistent, effective field theory from those that cannot be embedded in the consistent quantum theory of gravity. He has held position at leading research institute. Currently, he's a researcher at IFT and UAM. During the seminar, if you have any question, please use raise hand feature on Zoom, and I will give you speaking permission. Alternatively, you can send a question in the chat box. Now, I'm pleased to hand over the session to Professor Miguel Montero. Thank you again for accepting our invitation.
Okay, thanks a lot, Yashi. Let me just share content because very good. Excellent. So we have that. All right. So welcome everybody. Thanks so much to Daniel and Yashi for organizing this course and giving me the opportunity to talk about what I like the most, which is the Swampland program, and to share that excitement with some of you, I hope. So I think this is part of a longer course on black holes. So it's I'm gonna introduce the Swampland, but I'm gonna, throughout the introduction to the Swampland program that I'm gonna be giving in this set of lectures, I'm gonna be emphasizing also the connections to black hole physics. Okay, a lot of the Swampland program is actually motivated by black hole physics. Now, I think you actually already explained how to raise your hand to ask questions. This is just my name. These are the dates. So this is the first of 3 lectures. Here I have 2 references. So these are 2 lecture notes, 2 very nice sets of lecture notes for the, just put this here, for the Swampland program. So this one is by Eran Palti. It's a bit older, but more comprehensive. And there's the more recent one by Irene Valenzuela and other students, which came out of a school very much like this, and is more up to date, perhaps a bit more telegraphic. They're both very nice references. So if you're interested, if you want more details on anything that I'm going to be describing in the lectures, you can look here. Okay. Before I get started, there is something very, very important that I need to mention. And that very important warning is related to what I actually was explaining, is that you should please ask questions. Okay? Please ask questions throughout the talk. Interrupt me at any point. Just raise your hand. I probably won't be looking at the screen, but either Yashi or Daniel will let you. Please, anybody who has a question, just let them interrupt me immediately. That's, that way we get something a lot more interactive. The point of lecturing is not so much to, I'm going to tell you something you can read on a PDF. The point is that you can ask questions if I say something that is not clear. You can try to expand in whatever is interesting and is not being described here. That's really the point of having lectures, no? So try to take advantage of that. Ask questions, interrupt me, okay? And apologies if this is obvious to all of you. I just don't know the audience, so sometimes it's good to remind this. Sometimes people are like, yeah, don't worry, we're gonna interrupt you every 2 minutes. Please do that. Interrupting me every 2 minutes is great. Okay. Okay. So I cannot know otherwise if the lectures are adequate and useful. If asking questions live feels a bit awkward, you should try to do it. But if it's a bit awkward, you can also email me any questions. This is my email address, Miguel Montero at thesic.s. It's about the lectures or anything else I can help you with. So let's get started. Okay, so this is a lecture series on Swampland. So the first question, okay, whenever you're introduced to a new concept, 2 questions need to be answered. Number 1, what is this thing? And second, and equally important, why should I care about the thing? Okay. So to tell you what the Swampland is and why should you care about it, let's take it from the perspective of black hole physics. Okay. So you've been getting a course on black hole physics, and in a course on black hole physics, one typically studies Schwarzschild solution, different solutions, etc. One of the things that is typically discussed in a course on black hole physics is the Hawking radiation. Now let me ask. I'll start asking you. Was this covered at any point in the previous part of the course? Was Hawking radiation? Yes, perfect. Yes, okay. 20 yeses. Excellent. Thanks. This was a check to see I had not lost you already. That's perfect. Okay. So Hawking radiation, right? So we have the black holes emit energy, emit thermal radiation at a temperature given by the Hawking temperature. And I don't know if you guys want to just did the derivation. So in natural units is 1/8 pi m. That's the temperature. So the smaller, where this is the mass of the black hole, the smaller the black hole, the higher the temperature. And I don't know if you guys studied what's the temperature for astrophysical black holes. So for instance, one thing that you can check is that suppose you want to have a black hole whose temperature is in equilibrium with the cosmic microwave background, so 2.7 kelvins. You could ask, okay, what is the size of a black hole which has 2.7 kelvins as radiation? And the mass of such a black hole turns out to be roughly the mass of the moon. So it's very massive. And its radius, you know, for all the size that it has, because even though this is it's as strong a gravitational system as one can have is a black hole, its radius is just 133 microns. Okay, so you have this lot of mass. It's packed in a tiny region, and the quantum effects of gravity. Once you do that incredible thing of taking the whole moon and packing it to the size of 100 micrometers, still only radiates at 2.7 kelvins, barely noticeable, okay, comparable to the cosmic microwave background. So what this is telling you, okay, is that all that stuff that you've learned about black hole physics is extremely interesting. I, for one, love it. I'm very interested about it, but it is black hole physics, or at least quantum effects of black holes, or more precisely, quantum effects, are very far from being measured directly today. Okay? And why is this? Well, it has to do, the reason for this is that gravity is extremely weak. It is so weak that to make it strongly coupled and get quantum effects appear when one is sort of deviating a little bit from classical description. You need to go to a regime like this, a crazy regime where you have the mass of the moon in essentially like a pinhead. So that makes gravity very difficult to observe. There's other arguments you may have heard for this, for instance, when you're on the surface of the Earth, when you jump, just your jump is enough to momentarily overcome the gravitational force of a whole planet. So that's another manifestation of that weakness. So gravity is extremely weak, and it doesn't look that we're going to be able to measure it directly, certainly not its quantum effects anytime soon. Well, this is the naive expectation. This is what I have just given you is a argument that makes it sound reasonable and plausible that gravity, or strongly coupled regime of gravity, is not something that we're going to be able to access anytime soon. But it's nothing more than an expectation. Okay? Between an expectation and a proof, there is a big gap. And so what is the Swampland? That's the question I want to answer. What is the Swampland? So the Swampland, essentially, or the Swampland program, is based around the observation, which I'm going to spend the rest of the lecture describing, that, let me just, is the observation that subtle effects of gravity can actually leak to low energy physics. By low energy physics, I don't mean the physics of everyday life. I don't mean energy scales of, your everyday life, or even atomic physics, or even nuclear physics. But I do mean things like LHC, energy scales that perhaps we can observe today. So some effects of gravity actually can actually leak to low energy physics and lead to observable predictions. Observable predictions. So if you're someone who loves black holes, the Swampland is, I think, a very naturally attractive set of ideas, because it's telling you that a lot of the crazier stuff of black hole physics, quantum effects of black holes, they actually may be it's not thinking about black holes might not just be an academic exercise, might tell you something about, well, the universe that we live in, something that we didn't know before, something at low energies. Okay, so I think I told you more or less what the Swampland is and why should you care about it. So why should you care about it? Why should I care? Well, you should, because, if black hole physics can have implications for things like proton decay, masses and charges of particles, and perhaps even size of extra dimensions, things like the size of extra dimensions. All of these things are naturally very interesting, and they're quite important. So what I'm gonna do next, I give you like a basic idea of what is the Swampland. Is black hole physics can have implications at low energies. Next, I'm gonna tell you, still from a general perspective, but in a bit more detail, how this works, how people in the Swampland program work. How can it be, I'm gonna try to make it a bit more plausible that sometimes quantum gravity can have implications at low energies. So that's gonna be what I'm gonna be doing next. But before I do that, let me pause for a bit and ask if there are any questions about this very general high-level overview. Just the basic idea. You don't need to come up with super well-defined questions, okay? That's not the game. You cannot. I just gave you words. There was not a single equation yet. So try to think of questions about ideas, like how does this relate to something else that I know? Try to come up with a question. Okay, so let me tell you. Oh, is there questions? Oh, there's a question there. Very good, very good. Thank you so much. So we're gonna, excellent. 2 questions, excellent. So first question from Enrique is, so we're gonna meet QFT and Feynman diagrams. The next thing I'm gonna do is a Feynman diagram. The point of the course is not doing Feynman diagrams, so I'm just gonna draw it to you and roughly use it to explain the basic logic of how Swampland works, okay? Most of the effects, so there's some interplay with Feynman diagrams. They will also appear later in the course. A lot of the arguments that we have for this Swampland thing are non-perturbative. So we don't usually use techniques like Feynman diagrams, because Feynman diagrams are good, for instance, for perturbative quantum field theory. Even in quantum field theory, when you have a strongly coupled quantum field theory, Feynman diagrams have no use. So if you want to have a general argument about gravity, it better be more general. So the argument, Feynman diagrams are going to play a role. They're not going to be the main ingredient where we derive things. Now, the second question by Alexis is what controls this leaking? This is an excellent question. The answer is I'll answer this question later today for one of the Swampland constraints, but essentially the size of the leaking is controlled by the entropy of the smallest black hole that you can trust in your effective field theory. Imagine you have a very large black hole. Start making it smaller, 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 smaller. And at some point, the curvature radius of the black hole is gonna be so small that it's smaller than, let's say, that 1 over its size, its curvature is bigger than 1 TeV. When it's bigger than 1 TeV, you don't trust the effective field theory anymore, right? So you can keep pushing that to the regime where quantum gravitational effects become very important. The entropy of that black hole is going to control these effects on the Lorentz effective field theory. And the logic is that this black hole is going to appear quantum mechanically as a non-perturbative effect, leading to the breaking of symmetry. Very good, more questions. So can the Swampland live without string theory? I see we have someone who already has heard about Swampland. This is an excellent question too. So the this is also something I'm gonna comment later on, but a lot of the Swampland, okay, Swampland, you take two approaches. You, on one hand, try to find general arguments to black hole physics to motivate the things that you think are true about this leaking of quantum gravity to low energies. And once you have a general argument, you can just say, okay, I have a good general argument. I just go home. I'm so smart. I have a good argument. That's not good enough. You need to check. So what you often do is you check the things that you think are true because of general arguments against black hole, from black hole physics against concrete string theory constructions. Can the Swampland live without string theory? Yes, but it would be a worse life because there would be no way to check theoretically that some of these conjectures make sense. What string theory does for you in the context of the Swampland is gives you a good theoretical laboratory where you can check the Swampland ideas. The unfortunate fact is that as of today, there's no other framework that can substitute string theory for that, because other approaches for quantum gravity, like let's say loop quantum gravity, they are not at the precision stage which is necessary to check Swampland constraints. So Swampland constraints are precise statements about the effective field theory, and you need to have enough control of your quantum gravity to be able to access those details, and this is not always the case, and string theory is one example. Okay, more questions. Oh, sorry, I just got weird. Okay. So more questions. Is there some hope to see some of these quantum effects at low energies in experiments? Great question. So by the end of the course, I'm going to be discussing one conjecture, which is called the distance conjecture, and with some extra assumptions, okay? And for instance, one of the extra assumptions is some more things that are not just generic of black hole physics, they are particular of string theory, which is also related to the previous question. With these extra assumptions, yes, we hope so, And we also expect to see Swampland effects perhaps in cosmological experiments, although this is not completely clear. So yes, this is why people are excited on Swampland, because there is a chance to connect quantum gravity to experiments and to make predictions for today. Very good. And last question, is this just effect of gravity? To leak to low energy, very good, right? So you could say, okay, come on, certainly you can, in any quantum field theory, you just compute things in the UV, you just do computations, and you write a low energy effective field theory, and the IR parameters of the low energy effective field theory are a function of the things from the UV. So in that sense, of course, there is information from the UV inputted to the deep IR, that is for sure. The thing is that what is special about gravity is that it leads to correlations that do not typically appear in quantum field theory and which we believe are universal just from the fact that they come from gravity. People sometimes talk about UV-IR mixing as a way of relating these two things. There's a keyword you will find in some of the lectures on Swampland. But really what makes gravity special is its universal character. We believe there's no way to get rid of these effects, okay? Excellent, excellent. This is one I like. Lots of questions. Thank you so much, guys. Really appreciate it. Keep it up. Keep up the questions. So let's keep going. Let me tell you in a bit more detail how something like this works. And let's try to make our intuition, let me try to tell you why it's a bit difficult to imagine that, there's something like the Swampland constraints, something like gravity affects the effective field theory. To do that, let's think about how we couple gravity to an effective field theory classically. So first, switch off quantum effects. Let's make our life easier. And so how do we do that? Well, we just go to Wikipedia, we copy the Einstein-Hilbert action, and so we have gravity there, thanks Professor Einstein. And then on top of that, we need to introduce matter fields, okay? So, we need to introduce, let's say, the standard model Lagrangian, or maybe we are interested in some theoretical model just because we want to understand some theoretical model that is not exactly our universe, it's just similar, we're using it as a toy model to understand things. But in all cases, what you do is you take the Lagrangian of some matter, quantum field theory, and you couple it to this. How do you do it? Well, first of all, very important, you just put the square root of minus g in front of everything. So I'm going to put it here as well. And remember, when you couple to gravity, instead of, let's say, if you have a scalar field, which has an ordinary derivative, that's not good. You need to couple to covariant derivative, where covariant derivative here is the derivative minus the contribution of the Levi-Civita connection. And classically, if you want to couple any matter fields to gravity, you just do these things. You just do this, you just do this, bam. Any quantum field theory, there are some abstractions related to something called anomalies that appear at one loop. Let me ignore those. But ignoring that kind of thing, any quantum field theory you want can be coupled to gravity classically by doing like this. So when you put it like that, it seems there can be no constraints because, I can write any Lagrangian I want here. I can write any fields. I can give to those fields any mass. I can put any couplings I like. So it seems very difficult to imagine that you're going to be able to connect, oops, sorry about that, that you're going to be able to make universal constraints. But you should not forget one of the most important things about gravity, the thing that led gravity as being a spin 2 field, is this thing called the equivalence principle. Which in gravity is just a statement that gravity, in Einsteinian gravity is just a statement that gravity is represented by geometry. What this tells you is that gravity couples to everything. Okay? So what that means is that, when you have just that statement that gravity couples to everything at the classical level, is just a statement that you need to put the covariant derivatives like this. But when you combine it with quantum mechanics, what that means is that once you start taking into account loop effects, any coupling, if your effective field theory, is going to receive gravitational corrections. Okay? So for instance, if you have a 4-point function, there's going to be, for some scalar phi maybe, there's going to be corrections from graviton loops to this thing. Okay? If you want to get a mass, for instance, if a propagator gets corrected also by gravitons, but because gravitons also couple to matter fields, maybe this is some other matter field, so this is a graviton couples to some matter fields, you're going to get corrections by any other field in your theory. So everything quantum mechanically couples to everything else. This is unavoidable. This is because of gravity. In quantum field theory, you can put 20 copies of a Lagrangian of a quantum field theory. They don't talk to each other and it's fine. In gravity, they all talk to each other. And that means that competing quantum corrections, okay, they might be very tiny in the semi-classical regime of gravity, but it's going to be a mess. And when you go from the classical action to the quantum effective action, meaning you sum loops and try to write a semi-classical action whose equations of motion are the corrected equations of motion of the theory taking into account loops, you might end up, even if you start with something reasonable here, you might end up with something crazy. Maybe some couplings are negative in a way that violates causality, or all sorts of things could happen here. And that's at the level of perturbative Feynman diagrams. Non-perturbative effects that cannot be described by Feynman diagrams are also going to affect this thing. And so the point is that because gravity couples to everything, there is a possibility in principle that not every effective field theory, not every quantum field theory that you can write down, so perhaps can be coupled to gravity. The thing is that when we do something like GR plus effective field theory, we are doing this at the level of the IR, at the level of energies much smaller than M Planck. That is the only regime in which writing a Lagrangian of the Einstein-Hilbert kind together with a quantum field Lagrangian makes sense. And because this theory is non-renormalizable, we know it's not UV complete, it has to come from some UV theory that we don't know what it is. But because of the equivalence principle, we know these two things are tied together. You cannot UV complete this one on its side and then another one on that side, because that would lead to matter that doesn't couple to gravity. Because the two of them are coupled, it is possible that not every quantum field theory can be coupled to quantum gravity. So that leads to a picture. It's a famous picture you see in every lecture on Swampland. So you draw a big blob, and this big blob is the space of quantum field theories. It's a big blob, represents the space of all possible quantum field theories you can write down. N equals for Superior Mills, the standard model, infinite deformations of it, whatever you like. So it's an infinite dimensional space that you can write down. And they're all consistent quantum field theories by themselves. But if something like this is true, then the picture is that out of this big blob, only a subset of theories can be UV completed together with gravity. Due to string theory, and a lot of these ideas coming from string theory, there's something called the string theory landscape. The string theory landscape is the set of all string theory solutions. All those solutions give us effective field theories, which are here, because the landscape we know is effectives that are consistent, and so everything that is in blue can be can be coupled to gravity. So for instance, all string theory compactifications are here. And this blue region, oh, come on, sorry about that. I lost my edge with the blue. There are theories which are said to be on the landscape. Theories that are on the landscape, we say, can be UV completed in quantum gravity, can be coupled to general relativity. But the vast majority of theories, oh, okay, yeah, I just screwed that up. Let me just put the nice color. The vast majority of theories live in this green region, which is much bigger. Vast majority of effective field theories live in this region, which we call the Swampland. And effective field theories here cannot be coupled to gravity. So people who work on what is called the Swampland program, we essentially work here. We're right here. And we are looking at what delimits this fence. So we look for criteria. What are the criteria to determine whether a quantum field theory is in the landscape or in the swampland? So we go and say things like, for instance, a theory, let's say, with only very massive charged particles is in the swampland. Okay, so this is an example of one of the swampland statements that we're going to be describing. So for instance, this is related to what is called the weak gravity conjecture. But more generally, what we do is we come up with consistency criteria, which I'll call the swampland constraints. Okay. So the swampland constraints are statements with different degrees of support, of validity, that we believe.
Miguel, there are some questions in the chat.
Yes, yes, just 1 second. To be true generically. Please, let me see. Very good. Why the name of swampland? So the swampland idea originally came from Kunrun Baffa, and then another paper by Hiroshi Oguri and Kunrun Baffa. And so people had come up with the name landscape for all the set of possible effective field theories that could be obtained from string theory. Okay. And for a while, people were under the impression, because there's so many different consistent effective field theories you can get from string theory, they were under the impression that the landscape of effective field theories coming from string theory was so vast that every effective field theory could be put on the landscape. Okay, so they had this impression, and the original point of the swampland was to say, no, actually, no. You think of the space of all quantum field theories as this very nice landscape of theories, but actually most of it is not a nice landscape, it's bad, it's a swampland. So swampland came up as a contraposition to landscape. Landscape is where the nice theories are. Most theories are in the swampland. It's kind of like the landscape. A swampland is a kind of landscape, but it's a bad one. You know, it's like murky and it's not so good. That's where the name comes from. Can I give examples of familiar QFTs that belong to the swampland or to the landscape? Thank you. I should have done that. Very good. And it's related to the next question. What is the position of unequal force per Jan Mills? Very, very good. So let me see, for instance. So n equals 4 super Jan Mills. You should think of n equals 4 super Jan Mills as a quantum field theory by itself, okay? And you want to couple it to gravity. Let's say we take n equals 4 super Jan Mills with gauge group SUN, okay? And let's say, because we put the n equals 4 here, let's say that we want to couple it to gravity in a supersymmetric way. Because if I couple it to gravity in a non-supersymmetric way, because of this loop argument that I have here, it's not going to be n equals 4 super Jan Mills anymore. It's going to be non-supersymmetric. So it doesn't work. It has to couple supersymmetrically. And n equals 4 is a lot of supersymmetry. So I need to come up with a string construction or a quantum gravity construction that is of the form n equals 4 supergravity in 4 dimensions, and the matter theory is just n equals 4 super Jan Mills, let's say with gauge group SUN. So the answer to your question is that we believe, and this ties into a point that I'm going to make now, we believe that SUN for n less than 23 is in the landscape, and for n bigger than or equal to 24 is in the swampland. Okay? Now, why do we believe this? Okay? There is one of the conjectures that I'm going to be presenting. Since you asked, I will discuss this in the last lecture. There's one of the Swampland conjectures that we have is the Swampland distance conjecture. Together with supersymmetry, can be used to put bounds on the rank of the gauge group in theories with 16 supercharges, and these are 16 supercharges. And in 4 dimensions, this is what the bounds spit. Okay? So it would be against one of the Swampland conjectures to have SUN with n bigger than 24. Now, some of you might be thinking, but Miguel, come on, I know I can do ADS5 cross S5 is dual to n equals 4 supergen mils for any n. That is true, but that's holographic duality. You don't have n equals 4 supergen mils coupled to gravity, you just have a quantum field theory. And it's a quantum field theory which is all fine by itself. Okay, it's the difficulties coupling to gravity. We do have string constructions, for instance, compactify heterotic string theory on T6 that can get you SU23 gauge group for n equals 4 supergen mils. There's no way that we know how to get bigger than 24, and it goes against the expectations of the swampland. Okay, so that's, for instance, what we believe. Have we proven this rigorously? No. This is ties in what I'm going to be saying next, which is that what is the degree of support for the swampland conjectures? Let me get back to that in a moment. I'm going to keep on answering questions now. Let's see. So that's that. Yeah, one example of familiar QFTs belong to the swampland. Well, you know, n equals SUN for n equals bigger than 24. That's the position of n equals 4. So for those theories that belong to the swampland, the equivalent principles are not valid anymore. Well, this is a very good question because what I was giving you, okay, before with the loops and the equivalence principle is my motivation, okay, for swampland. So what I argued with that is that indeed it makes sense that gravity talks to everything, and because we don't have a UV completion of the system, it may be possible that you can have quantum field theories that cannot be UV completed to gravity. If there was no equivalence principle, you could have them by themselves. But I'm not sure if for each particular swampland constraint, I can directly connect to the equivalence principle. For one of them, I can. For the first one, the one that I'm going to be talking about today, which is the absence of global symmetries in quantum gravity, that one I can connect to the equivalence principle. Let's see. So do we have any estimate about the order of magnitude of the number of theories in the swampland in the landscape and the relative size? Excellent question too. Yes, the answer is we believe the swampland is a set of measures 0. Okay? So there's, in the space of quantum field theories, you can define natural measures. For instance, in the space of marginal deformations of a quantum field, foreign field theory and a quantum field theory, is something called the Samolosnikov metric. You can define a measure. We believe that the swampland is a set of measures 0. Okay, so they are really rare. So whoever asked this question, maybe asked this question because I drew it as a blob, like as a little ball, like this looks like a fried egg. Perhaps you should have drawn it more like this, like a line here, and 2 lines or something like that. It's a discrete set of higher codimension. I will make a note because there's an interesting paper by Kun Rumbafa and Jonathan Heckman that discusses this point. So I'm going to make a note, and on Wednesday, when we start the lecture, I will start by giving you this reference, which I don't have it right now, but I will just make a note. And in fact, you know, just well, the finiteness of the landscape with respect to the swampland has played a recent role in many investigations. Next question: is this 23, 24 for n equals 4 related to the critical dimension of the bosonic string? They are very close numbers. So, you know, I'm making this up on the go, so I should double check it. I think so, in some sense. So the 23, 24 that you can get for the rank, okay, for theories with 16 supercharges, you can get in some string theory constructions, and there's many ways to get those string theory constructions. One of the ways you can get it is by compactifying bosonic string theory. Compactifying, this is n equals 4, so it has to be superstring. So compactifying heterotic strings on T6 on just the product of 6 circles and go to a particular point in moduli space. Now, the heterotic string is in some sense a hybrid of a superstring for left mover fields and a bosonic string for right mover fields. For a bosonic string compactified to 4 dimensions, I need to have an internal CFT whose central charge is 22. I think one can view the 23 or 24 as coming from a situation where the current algebra is SU whatever that saturates this, okay? But I'm not sure. One will have to double check, but I think that's one potential connection. I think that's probably, I'll make a note to double check that and I'll get back to you on this. So central charge, bosonic. And okay, I'll double check. I think that's correct, but I'll double check. Okay, very good. Thanks so much for all the questions. Really keep it up. This is so much better. Okay, so the Swampland conjectures. Some of you ask, what is the, how sure am I that n equals 23 is in the landscape or in the swampland or so on and so forth? Well, that goes to the question of what are the swampland constraints? So what are they? And another question is, what is their regime of validity? Are they proven? So the answer to the first question is there's essentially the answer is go to the review. There are by now many swampland constraints people have identified in different ways. In this set of lecture notes, we're gonna focus on the 3 most established, and in the end, the 3 most powerful conjectures. Those are the no global symmetries conjecture, okay? So this is going to be the topic for today, after the high-level introduction that we are currently going on. The weak gravity conjecture. And the distance conjecture. So this is going to be for day 2, and this is going to be day 3. Roughly, it's more important that we have a meaningful conversation than to cover all the details of all conjectures. So maybe today we don't finish non-global symmetries and we keep with it on the second day, it's no problem. Very good. So these are some Swampland conjectures that we're gonna spend a lot of time discussing. So before we do that, let me answer the second question. What is the regime of validity? Are they proven? Well, the answer to are they proven is not in full generality. But think about what proving one of these conjectures would mean. We famously don't know a general framework to tackle quantum gravity. If we did, we wouldn't have to operate through indirect means or do semi-classical calculations, for instance, to derive Hawking's radiation. We would just get it from the sky. We currently don't have a framework to understand quantum gravity in general. So nobody can prove anything about gravity in general, which unfortunately we don't have that framework yet. Maybe one of you guys will figure it out, but it's not there yet. So the best that we can do is to have partial proofs. What do I mean by partial proofs? Proofs that are valid on very general, but not completely universal contexts, okay? For instance, we're gonna describe, for instance, today we're gonna talk about this no global symmetries conjecture. I cannot prove it in general to you, but I can argue it's true in ADS CFT. I can give a rigorous proof in perturbative string theory. So, you know, there's corners where of the space of quantum gravities where for one reason or another we have more control, and there we can actually get the things, we can prove them, some of these Swampland constraints, okay? So there's partial proofs for some conjectures, some of these Swampland constraints. Sometimes. But there's nothing that is fully general. There's one thing that comes close to being fully general that supports the Swampland constraints. We have, and it's very much in the spirit of this course, we have general black hole heuristic arguments. We are gonna see one of those in like 10 minutes. So you will get a flavor of it. These are essentially arguments that are short, they fall short of a proof, but they are appealing and they only use general properties of black hole Hawking evaporation. So you might believe they're true in any Einsteinian theory, but of course, you know, it's not a proof, there can be pitfalls. So on one hand, so what is the evidence for these things? So what we see is on one hand, we have proofs or partial proofs. But on the other hand, we have a lot of evidence which comes from string theory. String theory, theoretical lab. You know, people sometimes get into arguments, particularly on Twitter. This is a very popular topic of, is string theory right? Is the correct quantum theory of gravity? Is the other one the correct one? Do we have the correct one? Blah, blah, blah. Well, it is fair to say that we haven't found yet a concrete solution in string theory that describes our universe, that describes the standard model. It may be there, it may not be there, in which case the theory won't describe our universe. But what we know for sure, beyond any doubt, is that string theory is giving you concrete examples of fully complete, concrete, consistent models of gravity. Okay, so if you believe you have a general property of quantum gravity, like a Swampland constraint, that you believe is true in any quantum gravity, you can check it in all string theory models. And it better be true. If a string theory model falsifies your conjecture, it means you screwed up. There is at least one quantum gravity, maybe not our universe, but at least one quantum gravity where the thing doesn't hold, and so it doesn't hold in general. So these two things complement each other. We have partial proofs plus heuristics. And on one hand, so that's what we do. On one hand, people who work on Swampland try to prove Swampland constraints with partial proofs and heuristics. And on the other hand, you check in string compactifications. Let me tell you, checking in string compactifications is not easy because people don't just go one by one. They come up with techniques to check large classes of compactifications. So at the end of the day, you are involved in the use of sophisticated math of string theory to check some of these constraints. But when you show that the conjectures are true in very complicated setups, that actually gives you a lot of confidence because it's like, oh wow, this thing is true in many examples. There's a question. If a theory satisfies Swampland constraint, is it in the Swampland, in the landscape? If the answer is landscape, why is it called Swampland constraint? This is a great question. So I guess you could say it's a bit of unfortunate terminology. If the whole point of view of studying that there are some theories that you cannot apply to gravity, that you cannot couple to gravity. It's called the Swampland program. It's called the Swampland program because when the papers that, so the answer to your question is historical reasons, okay? So historically, the study of which theories can be coupled to gravity or not was understood as Swampland studies, like whether, some theories in the Swampland or not. So that's all Swampland studies, Swampland programs. And so when people came up with general consistency conditions for this, they were called Swampland constraints because the whole field was called Swampland. And so now we're in a situation where the constraints that tell you that the theory is in the landscape or not are called Swampland constraints. I agree with you. They should be called landscape constraints. but it's part of my job to sometimes when you're talking about a topic, you should use the nomenclature that it's used in the community, even if it's not the one that makes the most sense, because sometimes the nomenclature makes no sense. And if I just go about the landscape constraints, then you won't find anything on Google. Okay, another question. So do we say that a theory is on the landscape when it satisfies all the Swampland constraints? How do we know that there aren't more necessary constraints? Excellent. This comment is spot on. So we, indeed, in principle, what we would like to have, okay, let me just, because it's important, so let me just write it now. What we would like, and I emphasize like, to have is a full list of constraints. Just kind of like a checklist. And so I have my checklist of Swampland constraints. Number one, blah, 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 number two, blah, 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 blah. And so if you give me a theory and I just go and check it against the list, and if it satisfies all the elements in the list, it's in the landscape. If not, it's in the Swampland. We believe such a thing exists, but we don't have this yet. We don't have this yet. What we have is a partial list. Okay, so we just know some of the Swampland constraints in such a way that if one of the Swampland constraints is violated, you know that the theory is in the Swampland, but if it passes all the checks, well, you cannot be sure. It may be or may not be. To give you a concrete example, a little part of the Swampland community is focused on an example of a theory like this, is 5D n equals 1 pure supergravity. Okay, so this is an effective field theory you can write down, has a very simple Lagrangian. It just has three fields, has the metric, a vector field, and the gravitino. So it's a very simple theory. It's super nice, beautiful Lagrangian, but it's suspicious. We do not know how to get this theory from string theory. Of course, if you get something from string theory, that's one way you can be sure it's in the landscape. But this theory, we don't know how to get from string theory. And it passes also, so we don't know how to get from string theory. So we are not sure it's in the landscape, but on the other hand, it passes all Swampland constraints known to date. So this theory is a topic that you can hear conversations about in Swampland conferences because people are thinking, is trying to come up with arguments to understand if it's in the landscape or if it's in the Swampland. It's like a concrete toy model that people try to study. So that's an example of a theory where we don't know. Okay. Very good. So there we go. So we have the partial proofs plus heuristics. We have the string theory laboratory. Let me see if there's anything more high level that I want to tell you about. Yeah, so I think that's it. So what we're gonna do next, and we're gonna do for the rest of the of our time today, is we are now gonna dive in. So rest of the time, we are going to start our journey through the Swampland. We're gonna focus. Now things are gonna get concrete. We're gonna focus on the no global symmetries conjecture. So I'm going to be telling you what that is, what is the connection to black hole physics, okay, because so far black holes have appeared like in an ethereal way. I'm going to tell you what the connection to black hole physics is, and we're going to see what are the implications of this conjecture, which is, I think, a pretty cool topic. This is my favorite, or one of my favorites, Swampland conjectures. But since we're roughly at half time, and Daniel suggested to take a 5-minute break, let's just do that. Let's take 5-7 minute break. Everybody gets coffee or water or whatever, and then we're back. Excellent. Very good. So no global symmetry. So you've been listening to me for 1 hour about how cool the Swampland is. Let's just see a concrete example. Conjecture number 1, or constraint Swampland constraint number 1, no global symmetries. In quantum gravity. What does this mean? Let me just highlight it because it's nice and important. What does this mean? Well, first thing we should ask ourselves, what is a global symmetry? Well, perhaps, this is a question that you have all probably studied in your undergrad, master's, or whatever. A symmetry, it's a transformation that leaves the physics invariant. Okay, and we know, because of something very nice called Noether's theorem, that a transformation that leaves the physics invariant, a continuous one parameter family of transformations that leaves the physics invariant, leads to a conserved charge. So a conserved quantity. Very concrete example, suppose the effective field theory of a scalar field, something like this. Suppose it's a complex scalar field. So this Lagrangian is invariant if you multiply the field by a phase, like so. And according to Noether's theorem, this leads to a conserved current, which is called the Klein-Gordon current, and a conserved charge that you obtain by integrating over a spatial slice. This is your component of the current. This is all standard quantum physics. So this is all nice and well. This is a concrete example. But what if we want to talk about what global symmetries are, like very generally, without having to, go to a Lagrangian maybe? You might think, well, why can I not just always write the Lagrangian for my theory? Like, can't I always do that? The answer is no. For those of you that are not familiar with the concept, there are non-Lagrangian theories, theories which don't have a Lagrangian. They're strongly coupled quantum theories. And they're often interacting conformal field theories. They're very interesting. I'm just putting out the keywords so that if you're not familiar with those, you read about them because they're very cool. But that's why a lot of people don't like using Lagrangians for everything, because Lagrangians cannot capture the physics of every system. So it wants to be very general. It's not a great idea. From this point of view, one thing that is really a good handle on what a symmetry is the fact that it gives you a conserved charge. Okay, so symmetry of any kind is a conserved charge. And another way to distinguish what is a global symmetry is a symmetry that cannot be measured from far away. Okay, so symmetries typically, you have two types in QFT. Symmetries can be global, like the scalar example we just discussed. Oh, come on, I don't even know how to write global. Or they can be gauge. Okay, these are two very different examples of symmetries. We will say that a symmetry is global. We will say that symmetry is global if it cannot be measured from far away, and gauge if it can. Now, this may be a probably is a different description of the distinction between global and gauge symmetry than you're used to. So let me explain the connection and how the two of them are related. And to do that, let me take a process that happens in the real world. This is called beta decay. So a neutron becomes a proton plus an electron plus an electronic antineutrino. Okay, it's a very important radioactive decay. And in this example, okay, if you look at it as a process which is described by the standard model, there are actually two different conserved charges in this process. Okay, so the neutron has electric charge 0 and baryon number equals to 1. Proton has electric charge equal to +1 and baryon number equals to 1. Electron has electric charge equals to -1 and baryon number equals to 0. But it has another thing which is called lepton number, which has +1. And the antineutrino has charge equals to 0, but it's also lepton. And because it's an antiparticle, you gotta put a -1. So if you look at these charges here, what you see is that the electric charge is conserved. And B, the baryon number is conserved in this particular process. More generally, you can also see that B minus L is also conserved. Okay, B minus L is actually a symmetry of all processes in the standard model. Okay, of all of everything you can write down in the standard model. So B minus L is also conserved. So both these quantities are conserved, but they're very different in nature. Think of B minus L as just, if I give you a little box, I just give you a little box, okay? And I put some particles in there. B minus L is how many protons and neutrons minus how many electrons you have there, essentially. An electric charge, you all know what it is. It's just electric charge. So suppose I put some particles in this box. I take some particles. We have some charge and some B minus L. And I put them inside the box. And then, so the box has a door. So the particles go in. And then I just close the box. So the door is closed. So you cannot look in. And I ask you, what is the total B minus L inside of this box? There is no way you can tell me. Okay, there's absolutely no way. You need to go and open the box and count how many protons and electrons are there. If instead I ask you, what is the electric charge, you can actually tell me what's the electric charge inside of the box without opening the box. In fact, without getting anywhere near close to the box. Because of what? Because of Gauss's law. If there's some electric charge Q here, some net non-zero electric charge, because of the Gauss's law constraint, that means that the electric field in a sphere surrounding the box, even a sphere very far away, satisfies that the integral of the electric field is equal to the charge inside. So you can measure the electric charge from far away. Why can you do that? Because electric charge is coupled to a long-range gauge field. And couplings to gauge fields always come with these kind of constraints that ensure that you can measure the charge from far away. Now, for the case of the electromagnetism, you can just go and write down the Gauss's law. But the important thing is that this kind of feature, the fact that you can measure the charge from far away, it is the one thing which is universally true for any gauge symmetry. Okay, it's true for continuous abelian, continuous non-abelian, discrete symmetries. You can't always measure them from far away with a certain kind of experiment. Okay, like here is measuring the electric flux. For discrete symmetries, you measure instead an Aharonov bomb phase, but you can always measure it from afar. Okay, so a global symmetry is one that cannot be measured from afar, and a gauge symmetry is one that you can measure from afar by using coupling to gauge fields. So what the no global symmetries conjecture tells you, we now finally understand the statement, is that this one is okay in quantum gravity, and this one it isn't. That is, if you think you have a theory, an effective field theory with a global symmetry, and that effective field theory is coupled to gravity, then there's two possibilities. Either you were mistaken and the symmetry is gauge, or the symmetry has to be broken. So we're not going to describe how does that happen and what are the consequences in both cases. But before I do that, questions about the distinction. So what I've given you now is the statement of the conjecture. Now I'm going to explain what the consequences are, and I'm going to justify it. But questions about the statement in itself. What about mass as a charge? Excellent question. Mass is a gauge charge in this sense. Why? Because you can measure mass from far away using Newton's law, right? It's the same as the Gauss's law for electromagnetism. So you can measure from far away. It is related to the fact that we often say that gravity is a gauge theory. We say that gravity is a gauge theory, for diffeomorphisms. And in particular, in gravity, there is a constraint similar to this one, which is called the Hamiltonian constraint. Sorry, that was very badly written, but Hamiltonian. And the Hamiltonian constraint is what tells you that mass, in the sense of having a localized energy density, must source a long-range field, which is the gravity field. Okay, so do we say a theory is on the landscape when it satisfies all the landscape constraints? Yeah, this is the question of Martí that I already answered, I think, and then there's another new question from Martí. Does this mean that B minus L is not allowed in quantum gravity? Yes, what that means is that the standard, exactly right. This is a very good question. So you're seeing how Swampland can tell you something interesting about particle physics. So it's telling you that if you look at the standard model Lagrangian and you see a B minus L symmetry, you should say, well, that can be right. Either there's two possibilities. One, the symmetry is broken. So there are actually processes that break the symmetry, or the symmetry is gauge. And the symmetry is gauge, it means there is a fifth force that couples to it in the same way that the photon couples to electric charge. I will discuss this example in a moment. So if there's question, if it's not clear when I do that, please just ask again. So this means that all the conserved charges can't be measured from far away. Also, the conclusion that the global symmetries have charges that cannot be measured from far away has to do with the fact that it doesn't introduce interactions. Yeah, exactly. When you have something which has, it's a global symmetry, it means that states with different charges don't interact. So essentially, it's forbidding you of having certain interactions. The key reason why indeed gauge symmetry is different from global is because any gauge charge sources the gauge field, and the gauge field propagates its effect too far away. So I think it's the right intuition. Very good. So now let's follow through with Marty's question, actually, because if we buy this thing, for instance, that means that in the standard model, let me just, in the standard model, B minus L is a global symmetry. So what we are saying is that there's two possibilities. Possibility number one, it is actually symmetry is broken by beyond standard model effects, like non-perturbative effects. Okay. For instance, this is something that happens in grand unified theories. Grand unified theories are field theory UV completions for the standard model, where the standard model is embedded into a larger gauge group. And if, for instance, you have a gauge group which is SU5 or SO10, in the process of getting, there's another field like the Higgs field, which gets a VEV in a certain way. And so getting this VEV breaks some of the gauge group, and in particular, B minus L gets broken. Okay, so in grand unified theories, is an example of theories where this B minus L symmetry is broken. And this leads to experimental effects. So for instance, if B minus L is broken, there is a version of this process, which is called neutrinoless double beta decay, where you essentially can have this process without neutrinos. And that kind of process is allowed if B minus L is broken. So if the B minus L is broken, so that's one possibility. If the B minus L is broken, then you should observe this process. And people are looking for this process. Okay, they haven't observed it yet. The other possibility, so the possibility number 2, is that B minus L is gauge. That means that just like electromagnetism being gauge means there's a long range force, which is the electromagnetic force that couples to electric charge, this would mean that there is a new force. Can't be any of the existing forces because we know those don't couple to B minus L. So there's a new, what is called a fifth force that couples to B minus L. Okay, so this is also a kind of models that people study in phenomenology. For instance, once you have a long-range force like this, the important quantities is gauge coupling, the strength of interaction. This is known to be very small. Let me see. I have the number. Sorry. Let me just quickly see because I have the number around here. Sorry, guys. I have a bunch of files I cannot find. But the order of magnitude for this bound is, I think, 10 to the minus 24. Don't copy this. I will double check and correct. But it's something like this, okay? It's like 10 to the minus 20 something. So it's an insanely small number because people, what is charged under B minus L? Everything. I am charged under B minus L. You guys are charged under B minus L. So everything which has a different number of protons and neutrons and electrons is gonna be charged under B minus L. So most of matter, and we have measured forces within matter pretty accurately. So if there's a fit force and it has eluded or experiments, it has to be very, very weak. So, but this is one of the two possibilities. Swampland is giving you some information that just the fact that it's just like an exact symmetry, and the scenario where there would be neither neutrinoless beta decay nor a fit force is excluded. Okay, so it tells you something new at low energies. So that I think establishes is interesting, but why should we believe it? What is the argument? Why do we believe this thing? So why do we believe? Well, I told you before, the way we argue for Swampland constraints is by combining string theory arguments and different sorts of partial proofs and heuristics arguments. So for the case of the no global symmetries conjecture, it's one of actually the best established, the Swampland constraint for which there's more different lines of evidence. So for the no global symmetries conjecture, we have a black hole heuristic argument based on Hawking evaporation, which we're gonna see soon. Then there's also based on arguments of holography. There's calculations coming from the gravitational path integral, which is recent developments on how to compute essentially using Euclidean formalism the kind of Hawking effects that we have that can also give evidence for it, can be used to break global symmetries. And then there is, as I told you, a lot of evidence from string. So let's go for each of them in turn. I think for this course, I usually don't emphasize the black hole heuristic so much. So the black hole heuristic argument, it's very old. It's in a paper. You can read papers by Banks and Dixon. Banks and Dixon, 88. And there's also a very nice paper by Banks and Cyber in 2010. But the idea is as old as Wheeler, I'm told. As John Archibald Wheeler, which was the PhD advisor of Richard Feynman. So the idea of the black hole heuristic, I'm going to give you the heuristic argument, has to do with Hawking evaporation. Okay. So the heuristic argument for why there's no global symmetries. So we're going to try to give like some sort of argument that there's no global symmetries. So argument, and the argument that we're going to give is going to be an argument by contradiction. Okay, so we're gonna try to imagine what would happen if there was a global symmetry in a theory of gravity, an exact global symmetry, and then try to find a contradiction with the stuff that we know or we believe we know about black holes and global symmetry. So let's try to follow through the logic. Imagine I have a quantum gravity, so there is a quantum gravity with a global symmetry So it's given by a global charge. Let me call the global charge B. So it's just like baryon number before, but this may not be related always in a model. Where particle of lowest charge, let's say B equals 1. Let's just normalize our charge. Makes sense, right? Let's just say that the particle of lowest charge has charge B equals 1, has some mass M. And we take this mass to be lower than m black, so that the thing is not a black hole, but okay, it's a particle of mass. So now let's consider, the following, this is following, sorry about that, following Hedanken experiment. We take a cloud of particles, of this kind of particle, okay? So this is a cloud of particles, and there's n particles. So the total charge is just n, because we have n particles of charge 1, okay? And the mass of this object, the mass of this cloud of particles, okay, is, n times b, n times m, sorry, because each particle has mass m, okay? Now, suppose that we put this cloud of particles in such a way that the cloud undergoes gravitational collapse, forms a black hole. So now we have a black hole. Okay. Maybe we had to put a bit more energy when going in, and we don't know exactly, what's the mass of the black hole, but we know what the charge is. The charge is n. Why? I don't control the non-perturbative, formation process of a black hole, but I am assuming that I have an exactly conserved charge. Okay? If I have an exactly conserved charge, then by definition, I assume that whatever happens, the charge is conserved. So I have a black hole like this. And then this black hole, as you guys know very well, starts getting smaller and smaller and smaller by doing Hawking evaporation. Starts emitting Hawking calculation, Hawking particles. Okay? Now, here's one key point. You might say, well, so then my question is going to be, what is the charge of the black hole here? You could say that maybe it's smaller than n because some charge goes away in the Hawking radiation. But actually, to a very good approximation, the charge is n, because one can argue that because the Hawking radiation is thermal, it has an average B, which is 0. Okay? The only thing that this is saying is that the Hawking radiation is a thermal path, and on a thermal path, you have the same number of particles as antiparticles. So for each Hawking quantum with charge under the global symmetry comes out, an antiparticle comes out, and the average charge is 0. So this thing continues evaporating until it becomes a very tiny object. At some point, you know, Hawking's calculation is a semi-classical calculation, it breaks down. So all the mass is radiated away, and you end up with an object which still has B equals n, okay, and a mass, okay, which is maybe roughly of order m Planck. Let's say that's where the evaporation stops, when the black hole becomes Planckian. Now, the key point is that this object we have constructed is exactly stable, is dynamically stable, is exactly stable, cannot decay. Sorry, I seem to be having trouble with my iPad. So this object is exactly stable, okay? It cannot decay. Why? Because, you know, imagine that we choose the number n so large, that n times m, come on, n times n is bigger than m Planck. Okay? So n times m is bigger than m Planck. If this object here was gonna decay to elementary particles, because it has charge n, it would have to decay to a state with n particles of charge n. And the state of smallest mass of charge n, because it must have n particles, has a mass which is at least n times m. If my black hole has mass m Planck, it cannot decay to this guy. It just has less mass. So its decay is forbidden by conservation of energy. So the decay of the black hole is the decay of this small object is impossible. It cannot decay. Okay? So you end up to the conclusion. So you conclude you have an object of mass, of Planckian mass, okay? I'm gonna try something sometimes, because my iPad is acting out, I'm gonna open a new note. That sometimes helps. So I'm just gonna open a new note, and that typically helps. Let's see. So we have a black hole. Yeah. So we have an object of mass MP and baryon charge equals to n. Okay? And it's stable. Such an object is called a black hole remnant. It's called remnant because it's a remnant of the black Hawking evaporation. A Hawking evaporation process cannot get rid of it. Just from assuming that there is a global symmetry, we get the existence of remnants. But we don't get just one remnant, because this works for any n. You can take n equals, you know, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 4, any n that you like. And for each n, you're going to produce a different remnant. How do we know they are different? Because they have different values of the global charge. And if two states have different values of a global charge, they must be different states. And so we have, if we follow this logic, just from having a global symmetry, we have infinitely many remnants of mass and Planck. This is crazy, absolutely crazy. It's insane. Why is it insane? Because if we have these particles, they will run in loops and destroy our effective field theory. So imagine you want to compute, I don't know, whatever, any coupling, like a 4-point function in your effective field theory. There's going to be a contribution, which is going to be this thing, and then a loop of remnants. So I'm just going to draw it like black thick lines because they are remnants. Okay? And you're supposed to sum over all the remnants, and each of them gives the same contribution. And there's infinitely many of those. Why do you know that they give the same contribution? Because they're like black holes, the couplings are gravitational. And so this thing only depends on their mass, and they all have the same mass. So you have an infinity of black holes. So my coupling is infinity. The answer of any EFT question is infinity. This makes no sense. How can we avoid this? Well, we can avoid this if there are no global symmetries. If there is no global symmetry, I cannot conclude that I have infinitely many states, because the way I conclude these infinitely many states is because they are distinguished by an exactly conserved global charge. Okay? So you cannot have these guys. There are other variants of this argument. One that I like particularly is by studying the Unruh effect. So in that variant, what happens is that if you imagine yourself accelerating a little bit, the radiation that you get from the Unruh effect coming from just these remnants would be enough to burn you down at any acceleration. So it seems an instability of the theory. So I'm sorry for that argument. Let me give you a reference. It's called Trouble with Remnants. It's from 95 by Lenny Susskind. Okay, so that's another argument as to why remnants are bad. But the bottom line is that if you do not want to have these remnants because they ruin the effective field theory, looks like this, you should not have global symmetries. So you see, this is a black hole argument for the no global symmetries conjecture. It comes about by following the logic of what would it happen if you had an effective field theory with a global symmetry and concluding that everything goes down the drain. So you'd better not have this object. I'm going to explain next how a gauge symmetry avoids this argument, and what are the caveats of it. So I'm going to write it down so I don't forget. So how does gauge symmetry and caveats? But before I do that, are there any questions about the first argument for absence of global symmetries in quantum gravity? It's an important argument. I think it's quite powerful. No questions? It just follows from kinematics, and you need to, oh, very good. Excellent question. So Janek says it's not clear why the thermal radiation cannot take away the big charge. So let me be a bit more explicit about that. So the Hawking radiation, okay, it's in a thermal state. Okay, so in a thermal state. Okay, so in a thermal state, the state of the field, is given by the canonical partition function, right? So essentially, you have a state which is a sum of each pure state, projecting each pure state in the theory, and it's weighted by its energy. Okay. Suppose you have a global symmetry Q. Okay. If you have a global symmetry Q, what that means is that the Hamiltonian commutes with the charge, so you cannot. So the states with different charges, with charge Q and charge minus Q, have the same energy. So the Hawking radiation has the same probability. If you have a state with charge Q plus Q, it's weighted by e to the minus beta energy of the state. But if you have a state which has charge minus Q, it is weighted by the same thing. So it's the same probability to have a particle of charge 1 and particle of charge Q and particle of charge minus Q in the Hawking radiation. So on average, Q is 0. So on average, the Hawking radiation doesn't take away any charge. Now, even though Q is 0, the expectation value of Q squared in the thermal sample is not 0. So there are fluctuations. Every now and then, a Hawking particle, just by statistics, it happens that you emit 2 particles of positive charge, 1 particle of negative charge, okay? But the important thing is that because you know exactly what the Hawking temperature is, this expectation value is calculable. You can compute it, okay? And you can be like, you know what, I'm just gonna imagine that in the best case possible scenario, all the charge that comes out of fluctuations is getting away from my black hole. So you can compute this thing. And the thing is that for a very large black hole, because these effects are rare, the effect of charge going away by fluctuations is very subleading to the charge that you started with. So maybe it goes down by a little bit, but it doesn't have enough time to get rid of all the charge during the evaporation. So that's something that could have been a loophole to the argument, but isn't. Okay, so can you repeat the last point on the loop contribution of the remnants? Yes. So, and why remnants are stable? Okay, so let me start with the why remnants are stable. So I have let's say I have a remnant of mass. My assumptions are remnants have mass m Planck, okay, and a charge, a baryonic charge equals to n for some large number n, okay? And so, because the global symmetry is conserved, if this remnant were to decay to the vacuum, it has to decay by producing the elementary particles that I had in my theory. And the elementary particles in my theory have mass m and baryon charge equals 1. So if this black hole is going to decay into this kind of guys, it has to be a state with n guys because the charge has to be n. So that means that the mass of the decay product is m times n, okay? Now imagine that my n, imagine that my n is so large that m times n is actually bigger than m Planck. This could happen. It's not so weird to have objects in the effective field theory whose mass is bigger than m Planck. Any of you has a mass bigger than m Planck. M Planck in our universe is like a microgram, okay? You presumably are heavier than that. I certainly am heavier than that. And the reason for that is that I am composed of many particles. So my energy density is sub-Planckian, but because I take a lot of space, I can have a total mass which is Planckian, okay? So going back to our particles, because we have, if we are in the regime where m times n is bigger than q, that means that mass, this is the mass of the decay product, so mass of the decay, just by charge conservation, would have to be bigger than the mass of my state. So it's not possible to have this decay due to energy conservation. Okay? It's just, if you had this black hole and it would decay to these guys, all of a sudden you would have more mass, you would have more energy. Energy is conserved, even in asymptotic flat GR is certainly conserved. So no, it cannot happen. So that's why remnants are stable. Once the remnants are stable, why do I care about them, contributing to in loops and stuff? Indeed, this is one of the, let me tell you what is the argument that I made again, and then let me discuss the caveats, because here is one of the actual caveats of this argument. So what I thought was like, well, these things are like black holes. Black hole, you would imagine, couples to everything in the effective field theory because they can emit particles by Hawking radiation. So there's probably like some sort of like vertex, like a Feynman vertex, where this is like some sort of EFT particle. And here is a black hole or a remnant or line. And so if you have this kind of vertex, you can construct loop diagrams like this by just gluing 4 of these vertices. Sorry, this should be thin lines. So let me just erase that. So you can have diagrams like this, okay? And then so a black hole gives you whatever contribution it gives you, So this diagram gives you some, you evaluate the diagram with cutoffs and everything. And let's say the diagram evaluates to a value of, I don't know, some constant A. That's if you run one remnant in the loop. So this is remnant species number 1. But now you gotta take again the diagram and run it for species 1 and 2. So the contribution is 2A. But now this is species 1, 2, and 3. The label is the global charge. We have different remnants with different values of the global charge. 1, 2, 3, 4. So, in general, if I have n species, this goes like n times A. And because n is actually infinite in my theory, because I have infinitely many remnants, this is infinite. So it's a total breakdown of the effective field theory. You're overrun by UV contributions. Now, is this argument precise? No, not in any way. There's several things where you could try to avoid the conclusion. You could say, well, what if the remnants for some reason don't couple to effective theory particles? Or what if the Feynman rules for competing diagrams with remnants are different? Or what if the coupling is different for each remnant in such a way that the total sum is finite? Or what if I just add an infinite counter term like I do in renormalization and I get rid of this? Okay, so it's not a super conclusive argument. The fact is that when you have theories which have many states in the UV, they do correct the IR couplings. This is one of the themes in the Swampland, and this is an extreme version of that. I think the argument here is very nice. The argument here is more about, it's like, forget about Feynman diagrams. I maybe don't know how Feynman diagrams work with remnants. I'm just gonna imagine that I'm sitting in my car and my car has acceleration A. Then the Unruh effect tells you that I am feeling a temperature which is A over 2 pi in natural units. And this temperature is actually tiny because when you put the acceleration of your car in Planck units, it's really tiny, but it's telling you that you're actually feeling an effective field theory thermal state which has this temperature. Now, what that means is that you have some energy flux, which is of this form. But now, if you have the remnants, you should include the remnants. Now, the remnants have a Planckian mass. So if you have some temperature beta, which is 1 over A, the contribution of a single remnant is absolutely tiny because the M Planck is huge. So this factor is like exponentially suppressed. But if there's infinitely many of those, they will overrun your thermal distribution, whatever the temperature is. Okay? So that's the heuristic. If the answers that I give to your questions are not clear, you can just write so in the chat, like, can you clarify this, or can you clarify that? Okay, so you can also do that. But just to belabor the point, this is the heuristic argument. Why string theory? That's another question. Why string theory don't get infinite? Because of an infinite of an infinite tower of massive states in low energy. Very good question. Because we don't get an infinite tower. Okay, so the spectrum in string. Let me very good. Let me draw the spectrum. So this is the energy. Okay. And so let's just draw the spectrum of a theory with remnants. So this is going to be a theory with remnants versus string theory. So this is going to be string theory, a typical string theory compactification. So with remnants, we have, like maybe this is the little particle we have a mass m. And here at m Planck, exactly located at m Planck, we have 1, 2, 3, 4, 5. We have infinitely many states located at m Planck. Okay. And that's what gives us trouble, because however small the contribution is here, because they're all located at n Planck or within a very narrow band of n Planck, infinite times any finite number gives you infinite. In string theory, what you have is like the effective field theory states here, and at this point there's the string scale, and at the string scale you have a phase transition and you start having more and more states. You have an exponential density of states. So you have a lot of states, but they are like this. For any, there's a window. Okay, so the density of states is increasing, is denser and denser here, but on any given energy window, the contribution of the states is finite. So when you try to estimate the contribution of the stringy states to the effective field theory, is something more like you know, for this window, you have states which have energy e to the minus beta. For this, and you have n of those. On this other window, you have e to the minus 2 beta, let's say, and you have n2 of those, okay? And depending on what n1, n2, and 3 are, they're all finite numbers. Depending on how the energy density grows with temperature, this sum can be finite, even though there's infinitely many states. And that's what happens in string theory. The sum is finite. Here, we are in a very stupid example where it's just infinite on the nose, okay? People have also used non-arguments where they try to interpolate between this and that. They say, okay, fine, I'm gonna have something like a string theory spectrum, but with more states than string theory. Can I get constraints on the densities of states? Just by imposing that they don't overrun the effective field theory, and you can get constraints like this. But a string tower is not enough to overrun, okay? It won't give you anything. Okay. Let me give you now what is the biggest, in my opinion, the biggest loophole of this argument, okay? Which is that the mass of the little particles is different from zero. If I have a theory where the mass of my charged particles is zero, even the very small black hole, the remnant, can decay, okay? So it's not a great argument. So you see, I have this argument here that the mass of the decay product is bigger than m Planck, and that was because I assume I could take an n such that n times m is bigger than m Planck, but if m is exactly zero, I cannot do that. So that's a loophole to the argument. So it's not a great argument, okay? I think it's very good in that it makes you think, it makes you realize that, okay, maybe black hole physics can have implications on no energies. Maybe I should think about this more carefully, but it's not something you can turn into a proof. So to finish the lectures for today, and tomorrow we'll take it from, well, not tomorrow, on Wednesday, we'll take it from here. Let me now give you, now I gave you a very general, so above is a very general but heuristic argument. So what are my assumptions? Just essentially a particle with mass different from zero and black hole evaporating according to the Hawking process. So it's very general. We believe that's true in every theory. And now let me instead give you a less general but rigorous proof. Okay? I can give you a rigorous proof of the no global symmetries conjecture. And I'm going to do it in one context, which is that of the ADS CFT correspondence. So I'm going to be a bit more telegraphic here because the point of this is not give you a course on ADS CFT. It's just to give you an idea behind the arguments. If you want to have a lot, and there's actually a lot of subtleties and nuisances in these arguments, I'm just going to give you the simplest example of this. For the more general statement, you can look at the paper at one of the reviews I gave you, or the paper by Oguri and Harlow from 2018. Very nice paper. So I'm just gonna do the case for, I imagine I have a quantum theory of gravity in ADS. So the ADS CFT correspondence relates a quantum theory of gravity in d dimensions to a conformal field theory in d minus 1 dimensions. So what ADS CFT does for me is allows me to take problems in ADS, a quantum gravity problem in ADS that maybe I don't understand, and I can translate it into a quantum field theory problem in the CFT, and I have a lot more techniques, and I understand much better what a CFT or a quantum field theory is, okay? So what is the thing that I do in ADS? I imagine I have an ADS with a global symmetry, so some global conserved charge Q. And I'm gonna imagine that it's what it's called a U1 global symmetry. So a continuous global symmetry. What that means is that the charge is an integer, like the B that we're talking about. In fact, let me just correct that. And so that I don't change notations, I have a B here. That's my global symmetry in the ADS. Now, according to the ADS CFT correspondence, if I have a global symmetry in ADS, that means B is also a global symmetry in the CFT. But the CFT is a quantum field theory. We know a lot of global symmetries in quantum field theories. In fact, we started this lecture by discussing that whenever you have a global symmetry in quantum field theory, there's something called Noether's theorem that tells you there is a conserved current. Okay, it's a conserved current. There's a conserved current such that the charge is just the integral of the zeroth component of the current. Okay, I am cheating a bit here because of what I told you before about non-Lagrangian theories. Noether's theorem is strictly proven for Lagrangian theories. There is no proof for non-Lagrangian theories because Noether's proof uses a Lagrangian. There's also no known counterexamples, okay, of theories with a global symmetry which has a gauge, which has a current which is not gauge invariant on flat space. So there's no counterexample to that. So I'm just going to assume it's true in general. So if I assume Noether's theorem, I get that there is a current. But then, according to the ADS-CFT dictionary, the ADS-CFT dictionary tells me that for any operator that I have in the CFT side, I have a field on the bulk side that couples to it. And so they couple to something like this, phi times O. And in the particular case, when that field is a current, that means that in the bulk, there is some field, A mu, that couples like this. And conservation of the current, the conservation condition of the current implies that A mu is equivalent to A mu plus D lambda. Sorry, D mu lambda. Why? Because if I just change A mu to A mu plus D mu lambda, I get A mu plus D mu lambda times J mu, and that's the same as what I had before, plus D mu lambda, J mu, and if you integrate by parts, this is the same as the is the same as the integral. The second term is equal to the integral of lambda times d mu J mu, but that thing is 0 because of this condition. So I have, what I learned is that because of Noether's theorem, if I have some symmetry B, I have a symmetry B in the CFT is related to a conserved current. And this conserved current in turn tells me that in the bulk, there is a field, a vector field, which satisfies that A mu is the same as A mu plus D lambda. In other words, this is a gauge field. And in fact, this gauge field couples to B. So what that means is that we fail in producing a global symmetry. What that means is that this symmetry is gauge. So in holography, the moment I try to construct an exactly conserved symmetry, automatically, just from properties of holography and Noether's theorem, it comes out that the symmetry is gauged. You cannot ever produce a global symmetry. That would be a counterexample to Noether's theorem. So Noether's theorem in the CFT is the same as saying there's no global symmetries in the ADS. Okay? So that is a more solid, very general argument. It is not an argument I spelled in enough detail because it depends on, knowing what is the general dictionary of ADS-CFT, but it really uses the first things in the ADS-CFT dictionary. So maybe this is a good motivation to learn the ADS-CFT dictionary. Okay. So Noether's theorem in CFT implies for continuous symmetries, I only made this argument for continuous. It means no global symmetries in ADS. So we get an argument for no global symmetries, which is much more concrete, much solid. And it just uses essentially the Noether's theorem and the holographic dictionary. There are more arguments. There are more proofs. I can, so this is not completely rigorous proof because I didn't prove Noether's theorem away from Lagrangian theories. On Wednesday, we'll see an example where it's it's much closer to proof, although it's very similar in perturbative string theory. And then also discuss the string theory evidence for this thing, and the recent calculations using gravitational path integral that give evidence for this. Okay, and then we'll move on to discussing, okay, this statement maybe is true, but exactly in which way is it interesting? So I think I'll end here for today, since we are it's right around time. But I'll stick around for a bit in case you guys have questions about either this last thing that we discussed or any of the other topics in the lecture.